So in this video, we are going to look at the concept of shape of molecules and molecular angles. Please join and subscribe to my YouTube channel for more videos. So now I'm going to start with the introductory part. So the molecular geometry refers to the three-dimensional arrangement of atoms within a molecule. So as we know from the basic concept of chemistry, atoms join to form molecules. And even the molecules we have the giant molecules and we have simple molecules. So the molecular geometry is one of the area of chemistry that trying to determine the three-dimensional arrangement of atoms within a molecule. That is how the atoms are arranged in the molecules. So understanding the molecular shapes of the molecules, why do we need to understand the molecular shape of the molecules? Because it is one of the contributing factors that predict the physical and the chemical properties of a substance. So that is why by identifying or by knowing how the atoms are arranged in the molecules, and that will help or that will assist in determining how the molecules react as well as its physical properties. So behind this, there are various theories and models that help to determine the geometry and angles angles between the bonds or between the atoms in the molecule. And examples of this geometry or the shape of the molecules, it can be linear, it can be bent, it can be trigonal, it can be trigonal pyramidal, it can be tetrahedral, it can be trigonal bipyramidal. So there are different shapes of the molecules. And as we are going to look, or as we are doing the lectures, we are going to look at how these molecules form and how one shape of the molecules differ from one another and why are they differ from each other. So then the next thing is one of the theory and the model that trying to describe how the geometry or the shape of the molecules will be. So now starting with the valence shell electron shear repulsion theory. So this theory, that is VSEPR, is valence shell electron pair repulsion theory. So it's a fundamental in predicting the molecular shapes. And according to this theory, he stated that electron pairs repel each other, leading to specific geometries based on the number of bonding and non-bonding pairs. So generally, when molecules are formed, bonding and non-bonding pairs are usually generated. So according to this theory, the geometry of the molecules is based on the bonding and the non-bonding pairs. Like, for example, let me just give an example here. Let's say you have an atoms, and these atoms have atomic number. Let's say you have an atoms, and these atoms have atomic number or has an atomic number. Let's say 7. Nitrogen has atomic number 7. So you can draw the electronic configuration of nitrogen here as the first shell will accommodate 2, and then the second shell will accommodate 1, 2, 3, 4, 5. So don't forget that each and every element each and every element has its own way of writing it and its own classification based on the uniqueness of the atomic number of each element. So like, for example, we know that from the basic chemistry, we have different shells. We have K, L, M, and N shell. So for K shell, it accommodates a maximum of 2 electrons, while the L shell accommodates a maximum of 8 electrons. So you can see clearly here we have 2 electrons already here, and here we have 1 electron, 1 electron, 1 electron. So this means that from here we can see that this nitrogen atom needs only 3 electrons to become octets. So, but now the question is, how is this going to be acted? By either accepting electrons or sharing electrons. So where electrons can be shared here or can be actually can accept electron. Simple. We have one electron here. So therefore one electrons can be shared here or can be accepted. One electron here and one electron. So that is why, because they participate in bonding and they are called bonding pair. So those ones, they are called bonding pair. But because here it is already filled, there are two electrons there, so they usually not participate in chemical bonding, and that is why they are called non-bonding pairs. They are called non-bonding pairs. So according to this theory is a theory that actually try to demonstrate that the geometries, that is the shape of the molecules, is based on the number of bonding pair and non-bonding pairs. And very importantly, you can see clearly here in this figure, you can clearly see that we have the plane shapes as well as the bond angle. You see, we have linear shape, we have diagonal shape, and then also we have, like for example, this is a linear shape, and the bonding domain are 2, and then the non-bonding domain is 0. So it means that the bonding pairs are 2, and then the non-bonding pairs is 0, and it is linear, and the bond angle is 180 degrees. And examples of the molecules that have linear shape, we have carbon dioxide, we have beryllium chloride, we have mercury chloride. These are the examples of molecules that have linear shape. And then we have trigonal planar, that is the molecules that have three-sided. So we can see clearly here, this trigonal planar, at this point, it has 3 bonding pair and 0 non-bonding domain. And it is trigonal planar, and the one angle is 120 degrees, while examples of the trigonal planar, or a molecules that have trigonal planar, we have boron fluoride and sulfur trioxide. So these are the examples of molecules that have trigonal planar with 0 bonding domain and 3 bonding domain. And also we can have trigonal planar with 2 bonding domain and 1 non-bonding domain. So you see there are 3 still bonding pairs, but there are still 3 electrons. One is bonding and the other one is non-bonding. So there is a theory that demonstrated that the presence of non-bonding affects the geometry of the molecules as well as their bond angles. And as we do the lecture, we are going to see that. So you see, instead of the shape to remain trigonal planar, but because of the presence of this non-bonding domain is now changed to bent. Now the bond angles is reduced from 120 to 104 degrees centigrade. So these are the examples. We have ozone, O3, SO2, we have NO2 minus. So this is the examples. And of course, we have tetrahedral, that is those that have 4-sided. We have, first, we have the one with 4 bonding pair and 0 non-bonding domain. So it is tetrahedral, and the bond angle is 109.5. An example of this molecules, we have CH4, that is methane, and we have titanium chloride, and we have xenon of tetraoxide. And of course, in the case where the tetrahedral shape molecules has 3 bonding domains and 1 non-bonding, so the shape change from tetrahedral to trigonal planar. And that is why if you can even take the examples, the bond angle of course also decrease 107, and the examples we have NH3 and VHC and PCl3. So now if you can now take the tetrahedral, let's take carbon. So carbon have atomic number of 6. So if you can now look at it, you can see that the first one has 2 electrons, and then the second one will have 1, 2, 3, 4. You can see all of them, they are bonded. They are all bonded. So that is why in CH4, it is actually tetrahedral and the one angle is 109. So it's only in the situation where we have methane, one hydrogen share, it is electron, another electrons also, another atoms of hydrogen share electron here, another hydrogen share electron here, another hydrogen, and that is why we have CH4. So you see that you can see clearly here the carbon or the hydrogen bonded with all before bonding sites. So that is why it has tetrahedral shape, it maintained, and the bond angle is 109.5 degrees. But in a situation where there is non-bonding pairs, then the shape change and the bond angle also decrease. So that is how it happens. Like as I said in the case of ammonia, look in the case of ammonia, the nitrogen 7. So the first one have 1, 2. Here we also have 1, 2, 3, 4. So that is 1. There is one bonding pair. So that is the meaning of this one that is here. And that is why it is not maintained. It is tetrahedral shape and it is now changed to trigonal planar. Also in the case of water and OF2, you see there is 2 non-bonding. So if you take actually oxygen, you will see that oxygen has 2 lone pair of electrons or 2 non-bonding pair of electrons. So that is why the shape of water molecules is bent or V-shaped. So, ladies and gentlemen, I think from here you can see that it is very clear. So this theory simplifies the prediction of bond angles and molecular shapes based on electron pair arrangement. So that is the meaning of valence shell electron pair repulsion theory. So then, without wasting much of our time, let's look at the common molecular shapes. So there's some common molecular shapes that we have. We have linear shape, we have trigonal, planar, tetrahedral, and octahedral. So these are the common shape. These are the common shape of the molecular shape. So each shape corresponds to specific arrangement of atoms and bond angles. So the shape of molecules is influenced by the number of bonded atoms and lone pair of electrons. So that is why these are some of the examples. Like for example, the first one is linear and the electron pair geometry here, and then we have no lone pair. So if it is no lone pair, you see how the shape remain as linear. Then trigonal planar, then we have the shape is still maintained as trigonal planar, but when there is one lone pair of electrons, it changes to bend shape. Tetrahedral, the molecules, if there is no lone pair of electrons, it still maintained tetrahedral. But when one lone pair of electrons is added, then it's now changed to trigonal pyramidal. And when there is 2 lone pair of electrons in the tetrahedral molecules, then it means that it's now going to change to bend shape, whereby pyramidal or trigonal bipyramidal. So the shape, if there is no lone pair of electrons, remain trigonal bipyramidal. And of course, when there is one lone pair of electrons, it's now changed to Sawhorse. And when there is 2 lone pair of electrons, it's changed to T-shaped. And then when there are 3 lone pair of electrons, it's changed to linear. So ladies and gentlemen, what I wanted us to understand in the shapes of molecule or in the shape of molecules, the most important thing is to understand whether it's a lone pair or whether there is a lone pair of electrons or there is no lone pair of electrons. So the presence of lone pair of electrons affects the geometry of the molecules. So then the next thing is, let's start with each of the shape. So we have linear shape. So starting with the linear shape. So the linear molecules have a bond angles of 180 degrees. So their bond angle is 180 degrees. And these geometries occur when there are 2 bonding pairs and no lone pairs of electrons around the central atom. So that is why, ladies and gentlemen, it is simple and easy to predict the shape of the molecules as well as their bond angles, provided that you know that if there is no lone pair of electrons, the shape is this, and if there is the presence of lone pair of electrons, it will change to this. Like now, let me just give an example. Sometime you'll just be given a molecule and you will ask to determine what is the shape of that molecule. So it's simple. Like, let me take example of the CO2 here, we have CO here, or CO2. So if you can see clearly from CO, you can see that we have a carbon. So this carbon is directly bonded to one oxygen here and directly bonded to one oxygen here. So this directly bonding to oxygen, you add them, that okay, you have 1 plus 1, then we have 2. So it means that we have 2 electrons or 2 bonding pairs. And then the next thing, then you now count how many number of or how many lone pair of electrons are there in carbon. You can see clearly I demonstrated that carbon doesn't have any lone pair of electrons, so it means that it is 0. It is 0. So from here, you can even predict the hybridization of the molecule. So how do you do that? It means that since it is 2, you are now going to say 2 plus 0 is going to give us 2. So it's sp hybridization. You know that hybridization is when two different orbitals joined to produce a hybrid orbitals that have a desired or that have a specific characteristic that is different from individual one. So you see here, because it's 2, so it's sp, and it is trigonal, so it is linear, and then it is linear with a bond angles of 180 degrees. So then let's look at the trigonal planar. So in the case of trigonal planar molecules, the trigonal, they exhibit even angles of 120 degrees, and this shape rises from 3 different bonding pairs and no lone pairs of electrons around the central atom. So you see, this is boron. The atomic number of boron is, we have, of course, hydrogen, helium, lithium, beryllium, boron. So boron is number 5. It's number 5. So in the case of trigonal planar of the barium fluoride here, it doesn't have any lone pair of electrons in this case. So that's why it remains as trigonal planar molecule. So you see boron have atomic number. Boron have atomic number 5. So the first one have 1, 2, and then we have 1, 2, 3. So they are all bonding pairs. So one fluorine will come here, another fluorine here, share electron. So another fluorine. That's why we have Bl3. And of course, there is no any lone pair of electrons. So that is why it remains as trigonal planar. So then the next thing is tetrahedral molecules. So tetrahedral molecules, they have a bond angles of 109.5 degrees, and this their geometry is actually occurs as a result of 4 bonding pairs with no lone pair of electrons. So that is why it remains as linear. So it remains as tetrahedral with a bond angles of 109.5 degrees. But the presence of lone pair of electrons will be, of course, affected. And then the next thing is trigonal bipyramidal molecules. Trigonal bipyramidal molecules, they are molecules that have bond angles of 90 degrees and 120 degrees. So the trigonal bipyramidals, they have 2 bond angles, 90 and 120 degrees. So this shape results from 5 bonding pairs and no lone pair of electrons. So it's as a result of 5 bonding pairs and no lone pair of electrons. That is why we have this trigonal bipyramidal with a bond angle of PCl15. And then the next thing is octahedral molecules. So octahedral molecules, they have a bond angles of 90 degrees. So in this case, their bond angle is 90 degrees, and their geometry occurs with 6 bonding pairs with no lone pair of electrons on the central atom. And that is why it exhibits this octahedral shape. And examples of the octahedral is sulfur hexafluorides. So then the next thing is the effects of the lone pairs of electrons as discussed. I think I have discussed this, and let me just briefly also talk about it. So the lone pair of electrons can distort molecular shapes. You see, it will distort, it usually alter, it affects the shape and the bond angles. So this occur most because this occur more space than bonding pairs, so leading to repulsion and bond angle. So whenever there is this lone pair of electrons, it create more space than bond angles or than bonding pairs, and this leads to the repulsion of atoms and change in molecular angles. So for instance, in ammonia, NH3, the bond angle is approximately 107 degrees instead of the tetrahedral 109.5 degrees, and this is due to lone pair of electrons. So I think I also explained this image as the number of lone pair of electrons that keep changing. So then the next thing is the importance of the molecular shapes. So what are the importance of this molecular shape? One, these molecular shapes are important in chemical reactions. So the shape of molecules that determines which other molecules it can readily interact with and also react with, as only molecules with complementary shapes can effectively fit together and participate in the molecule. So you see, or in a reaction. So you see, in this case, the shapes of the molecules is what actually determine which of the other molecules will interact with it to undergoes a specific types of reaction to generate another product. So the shapes of the molecules is very important in aligning with other substrates for them to react, or with other reactants for them to react to, or to perfectly or effectively fit together and participate in that. So then the next thing is biological function. So living organisms, like the specific shapes of molecules like enzymes and receptors, are essential for their function, allowing them to recognize and bind to specific substrate or signaling molecules. So in the case of biological system, we have so many molecules that have their specific shape, and it's that their shape that make them to recognize their substrate in the case of enzymes, or a signaling molecules in the case of receptors. So it is very important. And once the shape of that molecules change, it means that the signaling molecules and the substrate cannot actually recognize by the molecules. So it's important in maintaining the biological processes in the body. So a molecule's shape can influence also the polarity, which affects its solubility in different solvent like water. So generally, molecules doesn't have the same pattern of, or the same polarity. Some are more polar than others, and that also due to the shape of the molecules. So it affects their solubility. Then the next one is physical properties. So molecular shape can impact physical properties such as melting point and boiling point sensing, the rest. So the the shapes of the molecules also affect the physical properties of the molecules, like in the case of the melting and boiling point, as well as sensing. So, in conclusion on molecular shape, so the shape of molecular, or the shape of molecules and its bond angles play a crucial role in its chemical behavior. So, understanding this concept is essential for fields such as chemistry, biology, and material science. So, the mastery of molecular geometry allows for prediction about reactivity, polarity, and intermolecular interaction. So, ladies and gentlemen, you should get this. You should understand that knowing the shapes of the molecules is very, very important. And please, if this is the first time you are coming to my YouTube channel, ladies and gentlemen, please try to join and subscribe to the YouTube community. Thank you very much, and see you next in our lecture series. And I hope you will find this video very interesting, and please share it to your friends. Please comment on the video. Thank you. Bye bye.